Right, so what I'd like to do is to take a little bit of a slightly random walk around RSA, some of the problems with RSA, look at some of the new cryptography methods, touch base with Chinese remainder theorem, because RSA is still open to that problem. There'll be a little bit of maths, not quite as heavy as Alan's maths, which is scary, but there'll be a bit of, because we're in the home of John Napier, well, not quite. He lived down the road there, but we'll pretend that we're in the home of John Napier. Then we'll touch base with John, and we'll try and understand cryptography. Okay, so I'm going to look at, is it the death of RSA? Some evil code, breaking crypto. I'll show you how I broke the internet, kind of. So I'll outline that. So all the examples are on that site, and go ahead and tweet if you want to. Okay, so I'd like to really look first at the death of RSA. So RSA is your true defender of your rights to your identity. Okay, RSA isn't used really in tunnels. When you're connecting to Google, you're using good old symmetric encryption, which Owen will crack in a little minute. But you're using that good old workhorse of AES. RSA is much too slow. RSA is used typically to prove your identity and also to prove the identity of Google. Okay, so it's your protector for identities. So we'll have a little look to see what the problems are. So this guy is Martin Gardner here. So Martin Gardner, very distinguished mathematician, and really is a real inspiration because he could tell you mathematics. He could explain mathematics to you, and you would actually understand it. There isn't many people around like that. I'd ask you to go and read some of Martin's work. Really inspirational. He wrote for the Scientific American at the time. And he had a column, and the column, in this case, it was mathematical games, was the paper. And it was these three, we won't call them hippies. It was about 1977. We'll call them punks. Punk was around then. I think I was just leaving school then. That was that long ago. And these three guys came up with an amazing concept that Whitfield Diffie had thought about and said, it will exist. A trapdoor will exist. I can create two keys where I use one key and only the other key will actually decrypt it. So Whitfield Diffie came up with that idea, but it was these guys that came up with it. Anybody tell me their names? Not for a prize? That's right. Okay. Who's your favourite? Oh, you can't see it on camera. Everybody likes Revest, but we actually like Shamir Islu here. We're really inspired. Shamir did a lot of that basic stuff. You actually find that most of crypto was founded in the middle 70s and hasn't really changed that much. I hate to say it, but it's still these guys who really created it. Okay, so he created, he set that column up, and in it he said, here's, if you're really interested, so they gave a little puzzle that you were to solve, and then they said at the time, why don't you contact us with a stamped addressed envelope, remember those days, before email, and we'll stick the paper in the post, and that'll be fine. So MIT will actually send that out. And obviously some people said, what's going on here? Oh, you can't do that. By which time it was too late. I think 30,000 of these envelopes had went out, and a lot of them went out to non-USA countries. But they came knocking on the door of MIT, said you've got to pull the paper, and they said, no. We have academic freedom. Our researchers have the right to publish. It's funded through a research grant, and we want to do it. So the tension was there already with this. And then they received letters such as this one. So this one here is said, you just cannot publish that. That cryptography is equivalent to a nuclear bomb to our enemies. You cannot publish that. So some people approached the IEEE at the time and said, do not publish this is dangerous work. So this is the letter that actually says that really it shouldn't be allowed to be published. And then there was other letters that came after that, saying it appears to breach the export regulations. Does anybody know what they did to stop it getting out of the US? What was the thing? And it's been the Achilles heel of SSL and the internet. Any idea what they did? They minimized the key length. How they did that, who knows? But Netscape, I don't know if anybody remembers Netscape here. They do. And AOL, that getting online with AOL, that was fun. So they limited the key to 512 bits, which Alan will tell you is easily crackable by your fridge. Not quite, but maybe your iPad from there. So they did that, and my God, has that caused problems. And so that was a 512-bit key size. And then Len Alderman at the time said, oh, I'll just stick my name on that paper. It's just kind of all right. He thought this wasn't really an important paper at all. And they put his name on it, and obviously it's been a highly significant paper. So that was the birth of RSA, and at the time, Ron in the interview, and when Martin Gardner was writing about this, they did a quick calculation, 63-digit prime numbers, which is kind of crazy these days, quite small, and they reckoned it would take 40 quadrillion years. So in the 1970s, that sounded like a long time, and I appreciate it does sound like that now. So there's an example of 78 digits. That's the kind of numbers that it actually comes up with. But so I've included the Stranglers who were around in 1978. I don't know if anybody remembers them. I certainly do. And Moore's Law, double processing power. I hate to say it, but if you half, by the time you get to 2015, 4 quadrillion years actually becomes 3,000. So that's the problem with crypto. That's the problem with crypto, is that after just a few years, because of the increasing power of the processor, then it becomes quite easy to crack it. So there's the team. That's the guys. That's the guys that we are really focusing on. Bob, good guy, bad guy, depends who you are, I suppose. Alice. Okay, we got to make sure that they can communicate with each other securely and that they prove their identity, because who can you trust on the internet? No one. Good. I'm glad you didn't say Google or Microsoft. So, or Facebook. We'll choose Facebook. So unfortunately, you've got to bring this guy in called Trent. Oh my God, Trent is PKI, public key infrastructure, digital certificates. Yuck. Disaster. Okay, this has been a complete and absolute mitigating disaster from there. And then, like it or not, you got to think like Eve, be like Eve, our Eve. Eve is our clown here. Okay, so Eve wants to pretend to be Alice. Eve wants to listen to the communications, and so on. So when it comes to evil code, so evil code and evil numbers. Okay, so we've all got our favorite evil number. 666 is one. So this is a real bus. I mean, who in their right mind said, well, okay, and the number of the bus 665 666. Okay, that's the bus of the evil. So we'll do that. So it's a real bus in the Far East. 666. 13. Actually, this Belgian airline had 13 dots. And had to repaint another dot on it just so it wasn't seen. People weren't getting on the flight because they counted the number of dots on it, and it was 13. So this is the problem. But the most evil of all numbers are prime numbers, as Alan will tell you, okay? 13, is 2 a prime number? Yes, okay. It's the shortest book in the world. Sorry for bringing in a joke. Shortest book in the world is the even prime numbers. It just says 2, end. So 13, 7, 23, 101. So in RSA, what we do is we take 2 prime numbers and we take 1 away from them and we multiply them together. And that gives us the core of RSA. If I can factorize n, then RSA is finished. So as Alan said, we've kept up with this because we've just kept making the numbers bigger and bigger, and we'll still keep doing that. But it gets to the point that it's a bit crazy. The most evil piece of code, I've done that. Has anybody done remove? Yeah, you've done it. Anybody else? Remove, yeah. Remove, don't do it now. Okay, don't do it. That's pretty evil. It just goes woof. And there's none of this undelete stuff. Undelete, it just, it's gone. Print hello, do while, that's pretty evil, and things like that. So those are evil. But there's an even more piece of evil code, and there it is there. So that's the Java code for RSA encryption. Okay, that is the most evil piece of code known in the universe. That is the code that terrorists can hide, and people that do bad things can actually hide from it. That is the piece of code that keeps most law enforcement awake at night. Okay? For us, it can be good because it protects our identity and we don't get scammers and so on. So we end up, cipher is equal to message to the power of E mod n, and message, when we decipher, we take D, take it to the power of D, and then take mod n, and everything's fine. We end up with 2 keys, E and then N, that we tell everybody. That's our padlock. And then D, comma N is what we keep private. N is not secret, but P and Q. Does everybody get that? You got that? Good. Right, so I'll show you a little bit of breaking crypto that was a bit unfortunate. And so here's how it works. We do two prime numbers together, P and Q. Okay, we take one off them and we end up with a value called phi. Okay, and we remember n, which is P times Q. So hopefully you're all following that. That's great. Right, this is the thing that gets most of our students, but they get there in the end, is that you've just got to find, I know you're looking for a formula here, but there's none. You just need to find something that doesn't share the same common factors between phi and the E, your encryption key. That's all you have to do. There's no magical formula here. You just have to find a number that doesn't share a common factor with 20. Can anybody tell me the factors of 20? 4, 2, 10. As long as we don't pick them, then everything is great. So we pick 3, and then we have our key pairs there. And we can go ahead and we can find out our decryption key. D times E mod of the phi gives us 1, and we can pick our E key. So that gives us our D and E. Then on the other side, when we cipher, we take the encryption key, and then when we decipher, we take the D key. And because we're in John Napier's university, then a lot of what is the focus of this is around discrete logarithms. And discrete logarithms are all about the difficulty of actually finding the original value when you raise something to the power of a value and then take a mod of a number. It's very difficult to find what that original value was. So the problem that researchers had initially in cryptography is that how does Bob and Alice get the same key? And the way it was solved was with this method here. So this is Diffie-Hellman's method. We take a value that both Bob and Alice understand or know, a G value, and we take a P value, and they both agree on that. Alice generates a random number A, Bob generates a random number B, Alice sends over G to the power of A, mod P, Bob takes that value, and raises it to the power of b. And through the magic of logs, if you remember at school, g to the power of a to the power of a is actually g to ab. And on the other side, Bob does the same calculation, and they end up with the same key. So this is the core of how we create a session key, how we get a key for every single session that we create. Okay, so I'll show you how I kind of broke the internet, and I apologize for this. If I end up cracking RSA, I certainly won't post it on LinkedIn and tell the world. I'll be going to the IEEE or ACM or something like that. So if you see something on LinkedIn that looks as if I've cracked something really serious, then it's probably not. Have a wee look. It'll probably say something like, this is a bit of fun, or this is just a little example, and so on. So I broke the internet, and here. Okay, so this was the article that I did, and it was a quick factorization of the values. So here they are here. I can show you the factorization. This was a little program I created, and all it really does, so I think I can crack that number there, hopefully. Good. So you actually find I can pick extremely large numbers, and I can factorize it for the two factors of it. Okay? I wasn't claiming that I'd cracked RSA at all. I could crack these long numbers, but certainly not the kinds of numbers that you would use in RSA. Okay, you can look at the article later. But then I got this as a tweet. So somebody thought that I had actually broken this. And then somebody went and changed my Wikipedia page to say that I'd actually cracked it. But then somebody else changed it to something else that maybe it wasn't. It says something like he doesn't know what he's talking about. So I think it was Richard that told me that this had been changed there. But it wasn't really a real crack that I'd done. It was just really a demonstration of it. So one of the methods that's used quite extensively in cracking RSA is the Chinese remainder theorem, and it's still relevant. And the Chinese remainder theorem involves the solving of this type of equation here. So the x mod 3 equals 2, and so on. Chinese remainder theory can actually determine what the value of x is efficiently. So I can solve it here, and we can see here that for that equation, the value of x is 23. That will make that actually work. And this can be applied in cryptography. If we look at the three equations here, we get three people to encrypt a message with the same encryption key and look at the ciphers. If you actually go through the maths, it's possible for you to find out the value of m given the ciphers that are resulting in. And in this way, you can actually crack RSA because you don't actually, you know the encryption key, and you know you can solve for the value of x there. Okay, you can go through the maths, and the maths work, but it's a very efficient way of cracking RSA. So what about the new cryptography that's happening? So I think it was mentioned earlier about homomorphic cryptography. So why do I have to give away all my data to someone if they want to do a calculation? So if I want to calculate the average salary of everybody in this room, everybody needs to give me the values, and then I calculate them, which means I'm giving away data. So it's possible with cryptography and with homomorphic cryptography to actually do a mathematical calculation on the ciphers and get a result. With RSA, it's possible to multiply. I think that's the only operation that you can do in it. You can't add and subtract, you can only multiply. So you can go through this example here, but it's possible for Bob and Alice to create and cipher two things together, two numbers, cipher them, and then Eve can actually determine the result. and it can be decrypted. And there's the maths behind it. Again, it's based on John Napier's work. You can actually see there when you multiply them together, we can actually do it by just multiplying the values. And there's some really amazing code out there that does it in JavaScript. So this code here, if it was working, this code here will actually do the calculation in JavaScript. Just let me generate my key pair. Okay, that's what homomorphic keys look like. I can encrypt. Okay, there's my two values for 3 and 4. I can then calculate A plus B. I can then calculate A plus B times C, and then at the very end, I can decrypt the value, and I get it back again. So this is important because it allows us to be able to keep values securely, even though we keep them on the cloud. So the ultimate is that we end up with something like that. Eve wants to calculate the sum. It's possible for her to take the two values that are ciphered and still work out the answer. So when it comes to new cryptography, and there's a whole range of devices that are methods that are being proposed for quantum robust methods. And I think, as Alan highlighted, a lot of them are based on classical linear codes, data communication codes, error checking codes, and so on. So what we need to do is to create a puzzle that's so difficult for a quantum computer that it can't factor in a reasonable time. So if you're interested, this paper goes back to 1978, and it's the McLeish method. But we have examples of the keys. And what you'll actually find is a lot of these methods, the actual size of the key is much bigger. So the days of us having small keys like 1024 bits are gone. We might be looking at key sizes that are megabytes in scope. So that's one method, as was highlighted by both presenters today. The other method is to look at lattice cryptography. And then there is another one, unbalanced oil and vinegar, a method, again, based on a trapdoor function, and the difficulty of solving multivariate polynomials. If you have 5x plus 4y plus 6z and so on, if you have a number of them, it's actually quite difficult to find the value of x, y, and z from them. And then the last one is based on Ralph Merkel's work about having a tree of hash methods. But the method that's really taken off just now, and it's what Google are using and Apple to harvest data from devices, is what's called differential privacy. So the problem that you have with an SQL database is that if I'm not allowed to look at the salary of people in a database, but I'm allowed to look at the average, if I take 50 people and take the average and include you, and then I knock you off the search, then I can mathematically show what your salary is. Okay, so they have a key means, key anonymity, where I'm limited to key searches, but I can still find out exactly. In an era of big data, that's a big problem because you're releasing the core data from the searches that you do. So differential privacy is all about adding noise to the data that you collect so that you can collect data on, say, gender or the usage without actually revealing the core data and the person behind the data. And that's what most companies are interested in. They're not that interested in you per se, because they've probably got that information. They're more interested on usage. So differential privacy involves that half the people tell the truth and the other half of the people tell a lie. So they intentionally tell a lie. So in this case, the top group tell the truth about their gender, and then the bottom group flip a coin and say, I'm male or female. And it's not really possible to tell who's telling the truth or not from that. So differential privacy is all about actually not revealing the core data in there. So Google have implemented it in their Chrome browser. and they can harvest vast amounts of data from the users because they add noise into it. Okay, so that's one of the methods. And the last method is what's called commutative encryption. And commutative encryption involves that it doesn't matter in which order you use the keys. You can use the public key first, encrypt. You can encrypt with a public key and then encrypt with a private key. You can then decrypt with a public key and decrypt with a public key and the private key, and that works. Normally you've got to unpick the encryption as the way that you've actually put the encryption on. But commutative encryption allows you to put the keys on in any way. It's a bit like having a hasp that you put locks on, and you can take the locks off one at a time. So this is a method that you can use to book a ticket at the Edinburgh Festival. Basically, the theatre can actually create a whole lot of tickets. It then encrypts it with its own key. Okay, so we have here a whole number of seats that can be booked, A1 to A3. It then sends them over. The user picks one of the bookings and has picked A2 there. They then add their encryption key onto that and sends them back. The other side can't actually tell which seat you've actually picked, but they take their key off it and they send it back to the person, and the person will then decrypt with their own key. Did anybody get that at all? No. Takes a bit of thinking, but it does work. I have tried around the theatres, and they just no, we're not interested. we're like the old method. So this is called zero knowledge. This is the future. This is the way you reveal too much of your information when you actually do anything like book tickets and so on. Does that make good? Time up. Thanks. And that's me. Thanks very much.
Fantastic. So obviously, who has some questions? I can't believe that nobody has any questions. Yes?
How long do we have left to use RSA for its publicly crackable?
How long left?
So the question was for the video is, how long do we have left before RSA is rendered obsolete?
I personally think that RSA is almost obsolete because nobody understands how it works. I've seen crypto teams and banks, and I've spoken to so many professionals, and they have no clue about how RSA and public digital certificates actually work. So I really think we need to change to something quite soon. Probably Alan has got a better estimation.
A lot of it obviously depends on when teams like Discrete come up with viable quantum computers, but we have made a standard in our paper, which is probably 10 years most. But I think anybody that, if they're building a new system, if they were to go for RSA now, would probably be a bit silly, because it's known to be slightly... It's worth saying about RSA that there is no... It's not provably secure. There is no formal proof of the security of RSA. All we know is that it doesn't appear to have been cracked yet. But we know there are some, like, the Chinese remainder theorem, the thing we were talking earlier on. There are plenty of classical algorithms out there for factorizing, so who knows? I mean, personally, I wouldn't use it.
Who has another question? Yep.
If we wouldn't use RSA, what would we use?
So the question was, if we don't use RSA, what would we use?
One of the 4 methods that were that were outlined there. So Google implement a new quantum robust method in Chrome. You can download the test Chrome app and have a look at it. I'll distribute the screenshots of it, but you can actually see the quantum keys. They've taken their own method to do it, but this is them experimenting. So if Google are doing it, and we know of many law enforcement, security or agencies that are really interested in creating applications that use it. So it is happening. Google I've got a prototype now.
So can I just add something there? I mean, if you want to see, then we've actually done a review in the paper, which is worth reading. The one that's showing the greatest promise at the moment, the lattice-based, and in particular a thing called ring-based, but ring with learning with errors. So if you look up ring LWE, you'll find, and the one that Google have released is a variant of that called New Hope, and they've actually put it to their TLS suite. So it's actually there now. But there are plenty of others. Google NTRU, there you go. The only problem with NTRU is there are various patents on it. So people are wondering whether there's a good idea to use that. And also, LWE has some advantages from a performance point of view. At least, as you say, the key sizes are so large. The UOV ones, again, it's the provable security. It reduces to something that we think is provably secure, but we're not absolutely certain, which is why I think a lot of people really are looking at the lattice-based ones.
And if you're into Python or Java, we've actually included source code for each of the methods. This is a Java one for the unbalanced oil and vinegar rainbow method, and we've got the Python code that allows you to do the lattice one. So we went ahead and actually implemented. It was really difficult to find source code, and we had to mix between Python and Java to actually get it. So if any students are looking for interesting projects, then this is a really interesting one.
It's worth saying, if anybody is interested in doing any research or actually building something, despite the fact that everybody knows you've got to go to these post-quantum, and there's a lot of theoretical work out there, in terms of actual implementation, there are relatively few. I think Bill's site was probably the first one that had the sort of the full set.
Do we have one final question?
So the other side is, like you think of something like online shopping or banking, it's not just about encryption, it's about proving identity as well. Can these algorithms do that kind of thing in RSA?
Some yes and some no. Things like NTRU, the lattice-based ones, in fact, not so very long ago, there was an NTRU signature-based scheme that came out. But it's a good point. One of the ways that certificates and proofs of identity have grown up with RSA, people have sort of begun to think of them as kind of synonymous, and they're not. So signature schemes and encryptions do need to be approached differently. And it might well be that certain candidates for post-quantum crypto turn out to be, that they might be a slightly different candidate for the signature scheme.
But I think public key generally focuses on identity anyway and signing things. So it's all about signing and proving identity. So I think AES is unbeatable in terms of performance and will never be beaten. So this is really hashing methods and signing.
Yeah, and it's worth pointing out, of course, we talk about public key encryption. For most dialogues, say in an e-commerce situation, the public key encryption is only used for the first part. Effectively what you're doing is encrypting the key that you exchange and then use symmetric AES or something like that. So, which is much more efficient, because public key encryption by its nature is very inefficient.
Yes, absolutely.
Okay, thanks.
Was one final comment? Elias?
Can you tell us more about this Google's quantum resistance?
I've got a LinkedIn article on it and how you actually find it. I could demonstrate here, but I wouldn't be able to find the parameters for it. It's somewhere like.
Do we know if it's production ready or tested? Or
Yeah. Well, they're testing it on you. You get and I just can't remember where the settings are for it. Just have a look in there. Don't you just love Google for their settings in Chrome?
I think it's got a search.
It's got a search. What we're looking for. Give me help. Give me help here, Elias. I'll publish it. There is a setting there, and you've got to. Sorry, you've got to download another app. It isn't Chrome. It's another version of Chrome that looks like Chrome.
By the way, that was the first question that is not
Fantastic.
Somebody watching will learn.
Excellent, excellent. Thank you very much.
Okay,
So big round of applause for Professor Buchanan. Thank you very much.